Thank you very much for the introduction. So the main theme of my presentation is to show you that if you take quantum systems, like spin waves, transitions in atomic vapors, and couple them to mechanical systems, microelectromechanical systems, then maybe you can improve the accuracy of MEMS oscillators and their stability, and at the same time take advantage of kind of very precise oscillations in the quantum systems. So there are many examples of quantum sensors you may be familiar with. Atomic vapor, magnetometers, or optical Qubits is another one. Very active sensors, another one. Polarization. These are topological devices that are exploring more qubits and also sensing. Semiconductor quantum dots that has been there for a long time. And defect-based sensors. So the specific example that I'm going to mention today is based on defect-based quantum sensors. So these are defects in diamond. They're color sensors, nitrogen-vacancy centers, and they kind of constitute a spin-1 system. And I'll explain what I mean by spin-1 system. But in a nutshell, you can pump them using green laser, and the defects have ground state. The ground state is turbulent, so it can be either 0 or plus or minus 1 spin state. Now, going between these different states, you can see some evolutionary oscillations between spin up and spin down, and that can be used to construct clocks and oscillators. So that's the one that we're going to mention today. So token-based is kind of a subcategory of defect-based, and phosphorus 31 is still has been there for a long time, and people are developing it as a qubit for quantum computers. And trapped ions is another example. There's a company, IonQ, that came up of Maryland, and they are constructing these elaborate quantum computers with trapped ions, and they are manipulating the state of the ions in order to, as a qubit, to perform quantum computations. And of course, nuclear magnetic resonance has been around for a long time. And there are many optical devices that are used for entanglement and remote sensing. So it's a short list of quantum sensors or quantum devices. The main capabilities of these quantum sensors is that they have very high sensitivity. So if you want to do, let's say, detect the magnetic field generated by brain firing, the neuron firings, that's on the order of the first type of sensitivity. So in general, quantum sensors and quantum systems are very, very sensitive. And they can also, perhaps if you develop the sensors, maybe you can also at some point start developing qubits. And of course, doing these at room temperature, as everybody is kind of goal. Most of these quantum sensors either require heating or evaporating the atoms for ions, ions and atomic vapor stuff, or they require cooling down in case of superconducting quantum current devices. So the question is whether we can come up with a hybrid system that takes advantage of the extreme sensitivity of quantum phenomena and robustness of and ease of use of microelectromechanical systems, and maybe things that are easy to use, but they have very high sensitivity. So one of the systems that is kind of gaining lots of popularity are these defect sensors in diamond. These are called zero phonon line defects. And the reason for it is that they're not affected by the vibration of the lattice in diamond. So there is a small temperature dependence, but even at room temperature, you don't need to cool them down in order to be able to use them for some useful either magnetic field sensing or electric field sensing or constructed quantum field. So my emphasis is going to be on this, and there are two different angles that I will explain. One is incorporating them in MEMS structures, and another one is to use, let's say, acoustic. It's also a MEMS structure, but has been around for since the 60s and stuff for radar signal processing and analog signal, very high frequency analog signal processing. And there is a new thing in there that I will kind of go over it, but I will kind of concentrate on these special defects in diamond and look at how we can combine them with MEMS as well as surface acoustic wave stuff. So if you look at a typical quantum sensor, it requires kind of a desktop or tabletop optics. Now this is simple one. It's a red reactor that we have set up. So there are two lasers. One is there, and the other one is left. You basically need 1 meter cube type of thing, maybe a little less, half a meter cube type of volume for setting this up. And in reality, you can integrate everything on a micro opto electromechanical substrate for about 1 centimeter cube type of thing. You can have a drop-in lasers. These are pixels, very small, so everything can be integrated either in hybrid form or true integration on a silicon wafer. So the whole thing can be put in there, and actually functionalities can be increased by right here. Adding so I just wanted to put that in there, and why people are interested, or should be interested, and we are interested in taking a desktop type of thing, or tabletop type of thing, and putting it on a silicon substrate. So going back to the zero phonon line, so I'll spend a little bit of time explaining what it exactly is. So everybody is familiar with diamond structure, and if you replace one of the carbon atoms with nitrogen, and this is naturally occurring dopant in diamond, and then put a defect in there, and the way they do that is they heavily look that they irradiate it with high energy electron beam, and then they anneal it so that these kind of get matched up. So you end up with a nitrogen and a vacancy, and then if you again you electron after you anneal it, then you can charge it. And these are called charged ME- charged nitrogen vacancy defects in diamond. So these have very special properties. These were, by the way, discovered in the early 90s. And it took till now for people to, actually there's a quantum computer that is being commercialized that is being sold out of Australia. You can buy these quantum computers. These are kind of room temperature computers right now, which is a major advancement in the field of quantum computers. So these can be used as qubits, and also they can be used as magnetometers, as magnetic field sensors. So there, if you take your that is about 5.5 eV from valence band to conduction band. These defects, they have their own band structure. So if you hit it with 532 move laser, you put lots of electrons in the conduction band, and as they come back, they populate these defect centers. And if the laser is not securely polarized, or if you don't do any special thing, eventually you start pumping in lots of electrons into the zero spin level of MV minus defect in diamond. So what you do then is you excite these electrons that are in the zero spin state. So that means that electron with the spin up is matched with the electron with the spin down. So the net spin is zero. If you hit it with 2.87 gigahertz, you can electrons with the spin up or down will go to specific spin states in the defect level. So you take it actually from here and put it in there. This is 2.87 gigahertz. And if there is no magnetic field externally applied, the spin up and the spin down levels have the same energy. But if you apply a small magnetic field externally, then you split these, because the spin up is like north-south in one direction and spin down is in the opposite direction. So if there's an external magnetic field, they attain slightly different energy. So that splits this level. So that's how you use it for magnetometry. So if you don't unpair the electrons, and if they're in the zero ground state of zero spin ground state of the defect, then the luminescence that comes out of the diamond is red. It's pretty widespread, but there is a very short one that's called zero phonon line. And this luminescence only is there if you do not compare the electrons in the minus ground state. If you apply the 2.87 gigahertz pulse, then you suppress this luminescence. So this is the basis of optical detection of magnetic resonance. So if you apply 2.87 gigahertz, then you take the electrons, compare them, and put them in plus minus spin state, and the luminescence goes down. So that's one key thing. It is the basis of optical detection of magnetic resonance, or electron resonance in this case. Another thing is that going from 1.8 Kelvin to 300 Kelvin, the magnitude of luminescence changes, but its wavelength doesn't change that much. So that's why it's called zero phonon light. It's not that sensitive to temperature. All right. So these are the levels that we will be working with. So now let me, for those of you who may not be familiar with MHz stuff, like most people are, these have been developed for a long time, actually, before 90s, but especially since early 90s, DARPA and other funding agencies, they have put in lots of resources into microelectromechanical sensors. The key idea behind MEMS structures and sensors is that by taking an inactive material, silicon is great material, but it's not optically active. There's no electric, it's not optoelectric. If you apply a voltage across it, it doesn't. You can, apply large voltage, changes practically work very hard. It's not like lithium niobate kind of stuff. So optically, it's inactive. However, if you take a silicon and if you pitch it and make it into thin plates, then you can use that thin plate as a little mirror. And by applying a small voltage, you can make it optically active. So that's the basic idea behind MEMS. Basically, use structures to take an inactive material like silicon and make it active. And usually it's for optics or pushing liquids around that, making tools out of it, and so on. So that is the basic idea of a microelectromechanical system. MEMS, which is very well developed, extensively can be fabricated and mass produced, and couple it with some atomic phenomena, either directing, let's say, atomic reference some directions for sensing and for enhancing its sensitivity, or with the diamond defects, since voltage, you're creating strain and stress inside that diaphragm, and then using that strain to change the energy levels in the defect. So, and then you can use that for manipulating the fluorescence that I explained. So, MEMS sensors, again, have been around for a long time. Actually, back in the 60s, people started with silicon, but it really took off from like around 1987, 1988. And there are tons of sensors that people have introduced, very, very exquisite sensitivities. And one of them is micrometers from. These are just examples that they're in this audience that they may get the sense, but these are some kind of canonical examples. A mass sensor, so you're going to vibrate this in resonance, and then the molecules come and sit on it, and resonance frequency changes. And we have shown that you can detect about 7 zeptograms, that's equal to very small atoms, using a simple candle like that as a microbalance. Or there are these very sensitive terahertz. These are critical polarometers, so their temperature changes, their resonance behavior change, and you can detect very faint terahertz signals, infrared signals, and so on. So the key is that the membrane that you're using for this itself is not sensitive. It doesn't change its conductivity or anything when terahertz comes in or infrared comes in. But you set it into vibrations, and then when something energy comes in terahertz or infrared, it changes as a Young's model, and that changes the resonant behavior of this happening diaphragm. That's how you detect the radiation. So you take a material that's inactive and make it into an active sensing material for the form of energy that you're interested in. So, so that's a little bit about MEMS and the key features of MEMS. They're easy to use, right? So they're like you put electric power in it, and whatever they sense, their output is in the form of electrical signal, although they can be other forms as well. They have people have shown that we can make them into devices very small when compared to their other other forms of implementations. They have a very high shock resistance. So since they're very small and near, I don't have much time, so I see that. Yeah. So these are the features of. So the key is that you can make them into very small devices, very robust format. So you can take those empty centers and you can incorporate them in a cantilever beam, in a diamond cantilever beam. And the key is that if you flex the this bridge, then you apply strain to these MV centers, and that changes those levels that I explained. And the interesting thing is that if for some reason by applying an RF pulse you flip these spins, that also applies a mechanical force into to that bridge. Sorry, my time is up. The key thing that I wanted to mention, and looks like I took more time than I should have explaining the background, is this. Recently, people have observed and that we are to surface based on non-magnetic materials, people have shown that they generate their own magnetic field. So there's electric material, and the atoms on the surface of the piezoelectric are slightly charged. So when the SAW comes in, surface acoustic comes in and passes by, it sends these atoms into elliptical motion, and that generates a magnetic field. So this magnetic field is actually pretty strong. It's on the order of millitesla or so at the surface, depending on the SAW power that you're using. And I really have to finish. So we use that in order to provide a feedback to. So we put the so these are the key results. So therefore, we can have a bilateral interaction between the surface acoustic device and the MV centers environment. So that is the significant, basically, observation. And then we can construct a SAW-based quantum computer by bringing these MV centers on the campus and having them interacted. So these are explained in detail in the paper. And the next step would be to put this on a bridge. I apologize